I want to look now at some properties of the Fourier transform. These are properties that are really useful when you're computing with Fourier transforms that help you simplify the calculations that you're doing with transformed functions. The first one is really simple. It's linearity. The Fourier transform is linear. So this means if you have two functions and you add them together, the Fourier transform, the sum, is the sum of the Fourier transforms. It also means if you have some function like f of t, the Fourier transform of a, some constant a times f of t, is just a times the Fourier transform of f of t. So, for example, here we have a sum of a Gaussian and a constant. The Gaussian here is multiplied by some constant a. The Fourier transform is the sum of the Fourier transforms of these individual functions. A second property is scaling and coordinate reversal. These two are closely related, as we'll see. So scaling, what I mean here is that rather than just, if we have some function of x, if we multiply x by a, so we're scaling the coordinate by some factor of a, then the Fourier transform is also scaled. In the frequency or Fourier domain here, which is k, going from x to k, the k coordinate is scaled by 1 on a, and the magnitude of the Fourier transform is scaled by 1 on the absolute value of a. So for example, if we have a Gaussian here where the x-coordinate here is scaled by a, then the magnitude is scaled by 1 on a, and this k up here is scaled by 1 on a, which gives us a factor of a squared here, along with this 4. Now we can also choose this constant a here to be minus 1. In this case, we have coordinate reversal. So f of x becomes f of minus x, and this becomes the Fourier transform function, capital F, of minus k, or in time coordinates, f of minus t becomes the Fourier transform, capital F, of minus omega. The scaling out the front here is 1 on the absolute value of a, so we do not pick a minus sign up out the front here. We just, if you reverse the coordinates in real space, you reverse the coordinates in frequency space without any extra scaling factor out the front. It's also very useful to know about the symmetry properties of the Fourier transform. So the Fourier transform here is written with this kernel e to the negative I omega t, but this kernel can be expanded as a cos omega t minus I sine omega t. Now the cosine function here is even, and the sine function here is odd, and this gives us some particular symmetry properties of the real and imaginary parts of this integral. So, if f of t is a real function, then f of t times cos omega t is all real. And the integral of f of t times cos omega t will be an even function because the cosine omega t just picks out the even parts. And this happened also for the Fourier series, if you remember, when we expanded even functions in the Fourier series, we had only cosine components. So the real part of this entire integral will be the even parts of the Fourier transform. The imaginary part here has the sine function in it though, so the imaginary part of this integral will be odd, because the sine function is odd. So if f of t is real and even, then the Fourier transform will also be real and even, because the odd part will be 0. And if f of t is real but odd, then the Fourier transform will be pure imaginary and also an odd function. I just want to spend a bit of time looking at this symmetry a little more closely. So if you have a real function in real space, in the Fourier domain, the real part of the function is even, but the imaginary part is odd. Now, if you flip the sign of the imaginary part of a complex number, then you're taking the complex conjugate. And here, an odd function, the sign is flipped as you compare the positive and negative parts of the frequency axis. And so what this means is this symmetry, another way of saying it is that the Fourier transform in the positive frequency domain is equal to the complex conjugate of the Fourier transform in the negative frequency domain. And this property tells you something about the meaning of negative frequencies, which is perhaps nice because the meaning of a negative frequency is maybe not all that clear. And so I hope just by saying a few words here, it may at least give you some intuition about what these negative frequencies do in a Fourier transform. So if you have a real valued function f of t, the negative frequency components of the Fourier transform must be the complex conjugate of the positive frequency components. So if you're comparing components at mirror image frequencies, that is plus and minus omega, then this Fourier component here is a complex conjugate of the one of its mirror image in the negative frequency part. And what this means is that If you have a real valued function in time or space, then there's a simple formula linking all the negative and positive frequency parts of the transform. They're not independent of each other. If you have the positive frequency components of the Fourier transform, the negative frequency components are just the complex conjugate. Now you know if you have a complex number and you add to that complex number its complex conjugate, you end up with a real valued number. In the case of this Fourier transform beast, what you have is a whole bunch of numbers on the positive axis and a whole bunch of numbers on the negative axis that are related as complex conjugates, and together they combine when you take the inverse Fourier transform to give you a real valued function in real space.